Hello and welcome back. Integration for the nation. A few tougher than normal definite integrals on the agenda. I will record probably about 10 to 15, but of course you won't see them in one go. A little bit spread out, probably one coming every kind of 4 to 5 days. And let's look at this integral here. Looks menacing, looks quite disgusting really. Definite integral from the square root of log 2 to the square root of log 3. And the integrand is 4x, the sine of x squared, over denominator sine x squared, plus the sine. Argument of the sine is the log of 6 minus x squared. Okay. The obvious thing to do for something like that, first of all, x squared, x squared, x squared, and the square roots in there is begging to say, look, let y is equal to x squared. dy by dx is going to be 2x, and dx is going to be dy over 2x, which will cancel this x there as well. And the limits will go from square roots to non-square roots. So that looks all logical. Even if you cannot see what to do next, this is something that kind of like, I like to think for most people that have done substantial amounts of integration at a much more involved level, is obvious. So this will now be y, and then we go sine of y plus the sine of the log of 6 minus y. And my dx is dy. I do apologize, you probably can hear, me manically chewing gum. My cough is not getting better. Somebody suggested to try chew gum. I'm so desperate at the moment, I'll do anything for the cough to reduce. So either you put up with a cough or with the chewing gum, or probably both. Okay. So far so good. So we got the log of 2 to log of 3 to sine of y over the sine of y. And definitely that is much more sensible than the original integral we started with, dy. Okay, now the next substitution is quite bizarre. I will talk about the substitution in more general form, but for the time I'm just going to do it, and then I will discuss it afterwards. Okay, the substitution that I'm going to use for something like this is let y, because that's the variable I got in there, equal to log 3 plus log 2, log 3 plus log 2, minus, I'm going to put a new variable, I don't know, v or something. So, or equivalently v, because it's symmetrical, log 3 plus log 2 minus y. And therefore, my dy is equal to minus dv. What happens to the limits now? That's the question. Log 2 and log 3. Remember, these limits are in y. So I'm going to get v limits now. So when I put log 2 in there, log 2 minus log 2 will cancel, so it goes to log 3. And when I put the other one for my y, log 3, then it will cancel the log 3s. So the limits, it looks like they swap. Okay, let's see what happens. So this is now a log 3 at the bottom, a log 2 at the top. And this now becomes 2 sine of y. Y is all of this. I'm going to write it as log 6 there now. Log 6 minus v. This will be exactly the same. The sine of log 6 minus v. And log 6 minus y will be, of course, plus the sine of v. And I'm going to have, of course, a minus dv. Just to save a bit of rubbing in space, I'm going to take this minus. Okay, so just dv and swap the limits back to that. Now, what just took place in there? I'm going to use a red pen, which might be a bit fat, but this is actually true for definite integrals. If and a lot of the time, if it suits you, or if you can see the tail signs, then you, of course, you should really be trying things like that. If you have an integral a to b, definite integral, of f of x dx, then this is always equal to the integral from a to b, f of a plus b minus x dx. So for example, and let me show you why this works, of course, because if you use a substitution, of course, here y is a plus b minus x, adding the two limits basically, then your dy is equal to minus dx. Look what happens. So at the moment I'm not putting is equal to, that's equal to whatever is meant to be equal to. First of all, now the x will become, because it's symmetrical, x is a plus b minus y. So that's f of a plus b minus y. The dx will become a minus dy. So let's put it as minus dy there, so we don't lose track. And when we're putting x is equal to a and x is equal to b, we have mappings. If we put x is equal to a, then we go y is equal to b. And if we put x is equal to b here, then y is equal to a. So the limits swap. But then if we look carefully in all of this, okay, then because we have a minus on the dy, we can throw it away. I could have actually here just gone and used the standard results, but you might be wondering, what am I doing? So I actually done it specifically for this particular function. And then of course the dy, the minus, will swap my limits. So we'll go back to a to b. And there's nothing special. I mean, the y is a dummy variable, so you might as well just call it x. Who cares? Saves like writing a substitution and just using another variable, which of course is that. And if you look at what happened in this particular integral, going from this line to this line, all that happened, it was exactly that. The limits stayed as they are. Okay, I called it v. I could have called it y and just saved myself a letter in all of this, but this is basically what I've just done in there. Okay, let me just rub off this particular thing. This is something that does come up an awful lot in higher level exams like STEP and AEA and I don't know, other exams in American exams, Indian exams, exams in Singapore and Malaysia. They have some quite specialist exams in math. So you will see it if you're involved with higher level integration with limits quite a lot. Okay, so what we got now so far, what are we going to do with this particular one? Now we're going to collect our results, because at the moment what we got in here, and it might not be obvious where we're going. So we're going to say the integral we're trying to find, and the integral, I'm not going to go right in the beginning. I'm going to go in the one that I use y's, which is log 2 to log 3, 2 sine y over sine y plus the sine of the log of 6 minus y dy is definitely equal to this integral here, which is in v. So let's see what that actually is telling us is happening in there. Sine of the log of 6 minus v over the sine of the log of 6 minus v plus the sine of v dv. We can call this integral I. We can call this integral I. It's the same integral. It has exactly the same numerical value. So I can actually use a dummy variable for both. So I can call everything in x. Let's say capital X. So or I can go use or something like that. Probably I'll go use. So I can say, you know what? 2 lots of my integral is equal to log 2 to log 3. So everybody's happy, is 2 sine u. I'm using u instead, it's no problem. Sine u minus u du. Okay, plus, we'll check that what we're writing is sound in a second. 2 times the sine, I'm looking at this bit here, log of 6 minus u over the sine log of 6 minus u plus the sine of u du. This is I and this is I. Okay, that's what we say. So that plus that, which I chose to write in use for simplicity, is 2 lots of I. What happens next? Well, 2I, first of all, we have a 2, we have a 2, we have a 2. Let's lose these 2. First of all, just I don't want to be carrying this stupid thing. It's gone. All right. So the integral I'm trying to find, which is I, is definitely equal that plus that, because I have exactly the same limits. So it's the log of 2 to log of 3. And it's annoying me having to write it again now. It's one way of making the videos a little bit longer. So one feels a little bit more important. Actually, I will put the du at the end. So that's this bit here, plus this bit here. Can you finish it off from there? Because I want to need to rub off, I'm afraid. I cannot quite fit what I need to fit in here. So that plus that du. Okay. The time it takes me to rub off, I'm going to rub off all of this kind of stuff except this line here. And as I said, the time it takes me to rub off, you should have finished this integral now. So I'm rubbing extra slow for that reason, to give you more time. Pardon me. All right. And look what happened here. Integral log 3. My integral, what I'm trying to find, is the integral from log 2 to log 3 of that plus that. But wait a second. We have the same denominator. That's interesting. Sine u. I'll write it like this denominator. Plus the sine of the log of 6 minus u. That's my du. And add the numerators. But if I add the numerators, I have exactly the same. Which means my integral is in fact the integral of 1 du, which will integrate, of course, to u from log 2 to log 3, which of course will be log 3 minus log 2, which of course, the best we can write this, is equal to the log of 3 over 2, with nothing else to say. I hope that was enjoyable. It was a little bizarre the first time I saw integrations like this. It took me a while for things to sink in, but I will do a few more of these, of this type if you want, so you can actually familiarize with that. Okay, till that time, I'm signing out, and keep doing maths. Bye for now.